3 o'clock, so let's get started. So I'm going to lecture today, give Andre a little bit of a break. So today last time we talked about we saw all the parts of ConvNets, we put everything together. Today we're going to see some applications of ConvNets to actually dive inside images and talk about spatial localization and detection. We actually moved this lecture up a little bit. We had it later on the schedule, but we saw a lot of you guys were interested in this stuff for projects, so we wanted to move it earlier to kind of give you an idea of what's feasible. So first, couple administrative things. Are the project proposals were due on Saturday. My inbox kind of exploded over the weekend, so I think most of you submitted it, but if you didn't, you should probably get on that. We're in the process of looking through those, so we'll go to make sure that the project proposals are reasonable and that everyone submitted one, so we'll hopefully get back to you on your projects this week. Also, homework 2 is due on Friday, so who's done? Who's stuck on batch norm? Okay, good. That's fewer hands than we saw last week, so we're making progress. Also keep in mind that we're asking you to actually train a pretty big ConvNet on CFAR for this homework. So if you're starting to train on Thursday night, that might be tough. So maybe start early on that last part. Also homework 1, we're in the process of grading. Hopefully we'll have those back to you this week so you can get feedback before homework 2 is due. Also keep in mind we actually have an in-class midterm next week on Wednesday. So that's a week from Wednesday. So be ready. That'll be in class. It should be a lot of fun. All right, so last lecture we were talking about convolutional networks. We kind of saw the pieces. We spent a long time understanding how this convolution operator works, how we're sort of transforming feature maps from one to another by running inner products by sliding this window over our feature map, computing inner products, and actually transforming our representation through many layers of processing. And if you remember, these lower layers of convolutions tend to learn things like edges and colors, and higher layers tend to learn more complex object parts. We talked about pooling, which is used to subsample and downsize our feature representations inside networks. So that's a common ingredient that we saw. We also did case studies on particular ConvNet architectures, so you could see how these things tend to get hooked up in practice. So we talked about Linnet, which is something from '98. It's a little 5-layer ConvNet that was used for digit recognition. We talked about AlexNet, that kind of kicked off the big deep learning boom in 2012 by winning ImageNet. There was an 8-layer ConvNet. We talked about ZFNet, that won ImageNet classification in 2013. That was pretty similar to AlexNet. And then we saw that deeper is often better for classification. We looked at GoogleNet and VGG that did really well in 2014 competitions that were much deeper than AlexNet and ZFNet and did a lot better. And we also saw this new fancy crazy thing from Microsoft called ResNet that won just in December in 2015 with 150-layer architecture. And as you'll recall, over the last couple years, these different architectures have been getting deeper and getting a lot better. But this is just for classification. So now in this lecture, we're going to talk about localization and detection, which is actually another really big important problem in computer vision. And this idea of deeper networks doing better, hint, we'll revisit that a lot in these new tasks as well. So far in the class, we've really been talking about classification, which is sort of given an image, we want to classify which of some number of object categories it is. That's a nice basic problem in computer vision that we're using to understand ConvNets and such. But there's actually a lot of other tasks that people work on too. So some of these are classification and localization. So now instead of just classifying an image as some category labels, we also want to draw a bounding box in the image to say where that class occurs. Another problem people work on is detection. So here there's again some fixed number of object categories, but we actually want to find all instances of those categories inside the image and draw a box around them. Another more recent task that people have started to work on a bit is this crazy thing called instance segmentation, where again you have some fixed number of object categories, you want to find all instances of those categories in your image, but instead of using a box, you actually want to draw a little contour around and kind of identify all the pixels belonging to each instance. Instance segmentation is kind of crazy, so we're not going to talk about that today. Just thought you should be aware of it. And we're going to really focus on these localization and detection tasks today. And the big difference between these is the number of objects that we're finding. So in localization, there's sort of one object, or in general, a fixed number of objects. whereas in detection, we might have multiple objects or a variable number of objects. And this seems like a small difference, but it'll turn out to actually make a be pretty important for our architectures. So we're going to first talk about classification and localization, because it's kind of the simplest. So just to recap what I just said, classification, one image to a category label. Localization is image to a box. And classification localization means we're going to do both at the same time. Just to give you an idea of the kinds of data sets people use for this, we've talked about the ImageNet classification challenge. ImageNet also has run a classification plus localization challenge. So here, similar to the classification task, there's 1,000 classes. And each training instance in those classes actually has one class and several bounding boxes for that class inside the image. And now at test time, your algorithm, again, makes 5 guesses, where instead of your guesses just being class labels, it's a class label together with a bounding box. And to get it right, you need to get the class label right and the bounding box right, where getting a bounding box right just means you're close in some thing called intersection over union that you don't need to care about too much right now. So again, you get it, for ImageNet at least, you get it right if one of your 5 guesses is correct. And this is kind of the main data set that people work on for classification plus localization. So one really fundamental paradigm that's really useful when thinking about localization is this idea of regression. So I don't know, thinking back to a machine learning class, you kind of saw like classification, like maybe with an SVM, and regression, maybe with linear regression or something fancier. And when we're talking about localization, it's really like we can really just frame this as a regression problem, where we have an image that's coming in. That image is going to go through some processing, and we're eventually going to produce 4 real-valued numbers that parameterize this box. There's different parameterizations people use. Common is x, y coordinates of the upper left-hand corner and the width and height of the box. But you'll see some other variants as well. But always 4 numbers for a bounding box. And then there's some ground truth bounding box, which again is just 4 numbers. And now we can compute a loss, like maybe Euclidean loss is a pretty standard choice between the numbers that we produced and the correct numbers. And now we can just train this thing just like we did our classification networks, where we sample some mini batch of data with some ground truth boxes. We propagate forward, compute a loss between our predictions and the correct predictions, backpropagate, and just update the network. So this paradigm is really easy. This actually makes this localization task actually pretty easy to implement. So here's a really simple recipe for how you could implement classification plus localization. So first, you just download some existing pre-trained model, or you train it yourself if you're ambitious. Something like AlexNet, VGG, GoogleNet, all these things we talked about last lecture. Now, we're going to take those fully connected layers that were producing our class scores. We're going to set those aside for the moment, and we're going to attach a couple new fully connected layers to some point in the network. This will be called, we'll call this a regression head. But I mean, it's basically the same thing. It's a couple fully connected layers, and then it outputs some real valued numbers. Now, we train this thing just like we trained our classification network. The only difference is that now, instead of class scores and ground truth classes, we use a L2 loss and ground truth boxes. Other than that, we train this network exactly the same way. Now, at test time, we just use both heads to do classification and localization. We have an image. We've trained the classification heads. We've trained the localization heads. We pass it through. We get class scores. We get boxes. And when we're done, like really, that's all you need to do. So this is kind of a really nice, simple recipe that you guys could use for classification plus localization on your projects. One slight detail with this approach, there's sort of 2 main ways that people do this regression task. You could imagine a class-agnostic regressor or class-specific regressor. You could imagine that no matter what class, I'm going to use the same architecture, the same weights in those fully connected layers to produce my bounding box. So that would mean you're sort of outputting always 4 numbers, which are just the box no matter the class. An alternative you'll see sometimes is class-specific regression, where now you're going to output C times 4 numbers. That's sort of like 1 bounding box per class. And different people have found that sometimes these work better in different cases. But I mean, intuitively, it kind of makes sense that the way you might think about localizing a cat could be a little bit different than the way you localize a train. So maybe you want to have different parts of your network that are responsible for those things. But so then it's pretty easy. Then it changes the way you compute loss a little bit. You compute loss only using the ground truth class, the box for the ground truth class. But other than that, still basically the same idea. Another design choice here is where exactly you attach the regression head. Again, this isn't too important. You'll see different people do it in different ways. Some common choices would be to attach it right after the last convolutional layer. That would just sort of mean like you're reinitializing new fully connected layers. You'll see things like overfeet and VGG localization work this way. Another common choice is to just attach your regression head actually after the last fully connected layers from the classification network. And you'll see some other things like deep pose and RCNN kind of work in this flavor. But either one works fine. You could attach it just about anywhere and it would do something. So as an aside, we can actually generalize this framework to localizing more than one object. So normally with this classification localization task that we sort of set up on ImageNet, we care about producing exactly one object bounding box for the input image. But in some cases, you might know ahead of time that you always want to localize some fixed number of objects. So here, this is really easy to generalize. Now your regression head, it just outputs a box for each of those objects that you care about. And again, you train the network in the same way. And this idea of actually localizing multiple objects at the same time is pretty general and pretty powerful. So for example, this kind of approach has been used for human pose estimation. So the idea is we want to input a close-up view of a person, and then we want to figure out what's the pose of that person. So, well, people sort of generally have a fixed number of joints, like their wrists and their neck and their elbows and that sort of stuff. So we just know that we need to find all the joints. So we input our image, we run it through a convolutional network, and we regress XY coordinates for each joint location. And that gives us that actually lets you predict a whole human pose using this sort of localization framework. This paper, and there's a paper from Google from a year or two ago that does this sort of approach. They had a couple other bells and whistles, but the basic idea was just regressing using a CNN to these joint positions. So overall, this idea of localization and treating it as regression for a fixed number of objects is really, really simple. So I know some of you guys on your projects have been thinking that you want to actually run detection because you want to understand like parts of your images or find parts inside the image. And if you're thinking of a project along those lines, I'd really encourage you to think about this localization framework instead. That if there's actually a fixed number of objects that you know you want to localize in every image, you should try to frame it as a localization problem, because that tends to be a lot easier to set up. All right, so actually this simple idea of localization via regression actually is really simple. It'll actually work. I would really encourage you to try it for your projects. But if you want to win competitions like ImageNet, you need to add a little bit of other fancy stuff. So another thing that people do for localization is this idea of sliding window. So we'll step through this in more detail, but the idea is that you still have your classification localization dual-headed network, but you're actually going to run it not once on the image, but at multiple positions on the image. And you're going to aggregate across those different positions. And you can actually do this in an efficient way. So to sort of see more concretely how this sliding window localization works, we're going to look at the overfeet architecture. So overfeet was actually the winner of the ImageNet localization challenge in 2013. This sort of setup looks basically like what we saw a couple slides ago. We have an AlexNet at the beginning, then we have a classification head, we have a regression head. Classification head is spitting out class scores, regression head is spitting out bounding boxes. And this thing, because it's an AlexNet type architecture, is expecting an input of 221 by 221. But actually, we can run this on larger images, and this can help sometimes. So suppose we have a larger image of, what did I say, 257 by 257. Now we could imagine taking our classification plus localization network and running it just on the upper corner of this image. And that'll give us some class score and also some regressed bounding box. And we're going to repeat this, take our same classification plus localization network, and run it on all 4 corners of this image. And after doing so, we'll end up with 4 regressed bounding boxes, 1 from each of those 4 locations, together with a classification score from each location. But we actually want just a single bounding box. So then they use some heuristics to merge these bounding boxes and scores. And that part's a little bit ugly. I don't want to go into the details here. They have it in the paper. But the idea is that probably aggregating these boxes across multiple locations can help the model sort of correct its own errors. And this tends to work really well. And I mean, it won them the challenge that year. But in practice, they actually use many more than 4 locations. Oh yeah, question?
So on the previous slide, so each of those red boxes, they weren't always within the slice being looked at. Is that just the design of the slide? Like normally the box would be fully within the...
Well, I mean, yeah, that's actually a good point. So once you're doing regression, you're just predicting 4 numbers. You could in theory predict anywhere. It doesn't have to be inside the image. Although that brings up a good point. When you're doing this, especially when you're training this network in this sliding window way, you actually need to shift the ground truth box in a little. You need to shift the coordinate frame for those different slices. That's kind of an ugly detail that you have to worry about. Yeah, but in practice, they use many more than 4 image locations, and they actually do multiple scales as well. So you can see this is actually a figure from their paper. On the left, you see all the different positions where they kind of evaluated this network. In the middle, you see those output regressed boxes, one for each of those positions. On the bottom, you see the score map for each of those positions. And then, I mean, they're pretty noisy, but it's kind of they're kind of generally over the bear. So they run this fancy aggregation method, and they get a final box for the bear, and they decide that this image is a bear. And they actually won the challenge with this. But one problem you might anticipate is it could be pretty expensive to actually run the network on every one of those crops. But there's actually a more efficient thing we could do. So we normally think of these networks as having convolutional layers and then fully connected layers. But when you think about it, a fully connected layer is just 4096 numbers, right? It's just a vector. But instead of thinking of it as a vector, we could think of it as just another convolutional feature map. It's kind of crazy. We've just transposed it and added 2 1-by-1 dimensions. So now the idea is that we can now treat our fully connected layers and convert them into convolutional layers. Because if you imagine in our fully connected network, we had this convolutional feature map, and we had one weight from each element of that convolutional feature map to produce each element of our 4096 dimensional vector. But instead of thinking about reshaping and having an affine layer, that's sort of equivalent to just having a 5-by-5 convolution. It's a little bit weird, but if you think about it, it should make sense eventually. Right, so then we take this fully connected layer, it turns into a 5-by-5 convolution. Then we previously had another fully connected layer going from 4096 to 4096. This is actually a 1-by-1 convolution, right? That's kind of weird, but if you think hard and sort of work out the math on paper and go sit in a quiet room, you'll figure it out. And so we basically can turn each of these fully connected layers in our network into a convolutional layer. And now this is pretty cool, because now our network is composed entirely of just convolutions and pooling and element-wise operations. So now we can actually run the network on images of different sizes. And this sort of will give us very cheaply the equivalent of operating the network independently on different locations. So to kind of see how that works, you imagine at training time, you're maybe working over a 14-by-14 input. You run some convolutions, and then here are our fully connected layers that we're now reimagining as convolutional layers. So then we had this 5-by-5 conv block that gets turned into these 1-by-1 spatially sized elements. So we're sort of eliminating, not showing the depth dimension here, but these, like this 1-by-1 would be 1-by-1 by 4096, right? So we're just converting these layers into convolutional layers. And now that they're convolutions, we could actually run on an input of a larger size. And you can see that now we've added a couple extra pixels to the input, and now we actually run all these things as convolutions and get a 2-by-2 output. But what's really cool here is that we're able to share computation to make this really efficient. So now our output is 4 times as big, but we've done much less than 4 times the compute. Because if you think about the difference between where we're doing computation here, the only extra computation happened in these yellow parts. So now we're actually very efficiently evaluating the network at many, many different positions without actually spending much computation. So this is how they were able to evaluate that network in that very, very dense multi-scale way that you saw a couple slides ago. Does that make sense? Any questions on this? OK, good. Right, so actually we can look at the classification plus localization results on ImageNet over the last couple years. So in 2012, Alex Kuchevsky, Jeff Hinton, Ilya Sutskever, they won not only classification, but also localization. But I wasn't able to find any published details of exactly how they did that. In 2013, it was the overfeet method that we just saw, actually improved on Alex's results a little bit. The year after, we talked about VGG and their sort of really deep 19-layer network. They got second place on classification, but they actually won on localization. And the VGG actually used basically exactly the same strategy that overfeet did. They just used a deeper network. And actually, interestingly, VGG used fewer scales. They stamped that network out in fewer places and used fewer scales. But they actually decreased the error quite a bit. So basically, the only difference between overfeet and VGG here is that VGG used a deeper network. So here we could see that these really powerful image features actually improve the localization performance quite a bit. We didn't have to change the localization architecture at all. We just swapped out a better CNN, and it improved results a lot. And then this year, in 2015, I mean, Microsoft swept everything, as that'll be a theme in this lecture as well. This 150-layer ResNet from Microsoft crushed localization here and dropped performance from 25 all the way down to 9. But I mean, this is a little bit this is tough to really isolate the deep features. So yes, they did have deeper features, but Microsoft actually used a different localization method called RPNs, Region Proposal Networks. So it's not really clear whether whether it's the better localization strategy or whether the better features. But at any rate, they did really well. So that's pretty much all I want to say about classification and localization. Just consider doing it for your projects. And if there's any questions about this task, we should talk about that now before moving on. Yeah?
How much are you limited by outliers in your data set? So if ImageNet has things that are incorrectly labeled or the boxes are in the wrong places?
Yeah, that can always hurt performance, especially with an L2 loss. Right? So then L2 loss when having outliers is actually really bad. So sometimes people don't use an L2 loss. Instead, you can try an L1 loss. That can help with outliers a little bit. People also will do sometimes a smooth L1 loss, where it looks like L1 sort of at the tails, but then near 0, it'll be quadratic. So actually swapping out that regression loss function can help a bit with outliers sometimes. But also, if you have a little bit of noise, sometimes hopefully your network will just figure it out. Cross your fingers. Don't think too hard. Any other questions? Yeah.
When we're using one of these pre-trained nets and just training the regression hat, as you call it, do we just backprop into our own regression hat, or can we backprop all the way into the
Yeah, good question. So people do both, actually. So for overfeet, actually, I don't remember. I don't remember exactly which overfeet did, but VGG actually backprops into the entire network. So it'll be faster to it'll actually work fine if you just train the regression head, but you'll tend to get a little bit better results if you backprop into the whole network. And VGG did this experiment, and they got maybe 1 or 2 points extra by backpropping through the whole thing, but at the expense of a lot more computation and training time. So I would say, like, as a first thing, don't just try not backpropping into the network.
Does that even generalize? I mean, the testing data can sometimes look pretty different from what these nets were trained on, right?
Well, yeah, generally not, right? Because you're testing them on the same classes that you saw at training time. So you're going to see different instances, obviously, but I mean, you saw bears at test time, you're going to see bears at training time. We're not expecting you to generalize across classes. That would be pretty hard. Yeah?
If you're backpropping the whole network, does that mean you then have to train with the classification head and the localization head simultaneously?
Good question. Yeah, so sometimes people will do that. They'll train with both simultaneously. Also, sometimes people will just end up with separate networks, one that's sort of only responsible for regression, one that's only responsible for classification. Those both work.
What if you don't know the number of objects that are going to appear in the image?
Well,
And then pick up all of them?
glad you asked. That's actually the next thing we're going to talk about. That's a different task called object detection. So, yeah?
Is there synchronization between the localization class and then the classification class?
Well,
separates, right? So
yeah. Well, so it kind of depends on the training strategy. It also kind of goes back to this idea of class agnostic versus class specific regression. So if you're doing class agnostic regression, it doesn't matter. You just regress to the boxes no matter the class. Class specific, you're sort of training separate regressors for each class. All right, let's talk about object detection. So object detection is like much fancier, much cooler, but also a lot hairier. So the idea is that, again, we have an input image. We have some set of classes. We want to find all instances of those classes in that input image. So, I mean, regression works pretty well for localization. Why don't we try it for detection too? Well, because in this image we have these dogs and cats, and we have 4 things. We have 16 numbers. That looks like regression, right? Image in, numbers out. But if we look at another image, then this one only has 2 things coming out, so it has 8 numbers. If we look at this one, there's a whole bunch of cats, so we need a bunch of numbers. So, I mean, it's kind of hard to treat detection as straight up regression because we have this problem of variable sized outputs. So we're going to have to do something fancier. Although actually there is a method we'll talk about later that sort of does this anyway and does treat it as regression, but we'll get to that later. But in general, you want to not treat this as regression because you have variable sized outputs. So a really easy way to solve this is to think of detection not as regression, but as classification. Right? In machine learning, regression and classification are your two hammers, and you just want to use those to beat all your problems. Right? So regression didn't work, so we'll do classification instead. We know how to classify image regions. We just run it through a CNN, right? So what we're going to do is we're going to take many of these input regions of the image, put a classifier there, and say like, oh, right, this region of the image, is it a cat? No. Is it a dog? No. Move it over a little bit. Oh, we found a cat. That's great. Move it over a little bit. That's not anything. So then we can actually just try out a whole bunch of different image regions, run a classifier in each one, and this will basically solve our variable sized output problem. So oh yeah, question?
So how do you decide what's the window size?
So the question of how to decide what the window size, the answer is we just try them all, right? Just literally try them all. So that's actually a big problem, right? Because we need to try windows of different sizes, of different positions, of different scales. We need to do this for every test image. This is going to be really expensive, right? There's a whole lot of places we need to look. Yeah?
Also here you're saying, like in your windows, does that look like anything? Or usually when you're classifying, you just take whichever class has the biggest score, right?
Oh yeah, so in practice, you usually also, when you're doing this classification, you add an extra, two things. One, you can add an extra class to say background and say like, oh, there's nothing here. Another thing you can do is do actually multi-label classification, so you could output multiple positive things. Right? That's actually pretty easy to do. It's just instead of a softmax loss, you have independent regression losses or independent logistic regressors per class. So that can actually let you say yes on multiple classes at one point. But that's just swapping out a loss function. So that's pretty easy to do. Right? So actually, like we said, a problem with this approach is that there's a whole bunch of different positions we need to evaluate. The solution, sort of as of a couple years ago, was just use really fast classifiers and try them all. So actually, detection is this really old problem in computer vision. So you should probably have a little bit more historical perspective. So starting in about 2005, there was this really successful approach to, at the time, really successful for pedestrian detection that used this feature representation called histogram of oriented gradients. So if you recall back to homework 1, you actually used this feature on the last part to actually do classification as well. So this was actually a sort of the best feature that we had in computer vision circa around 2005. So the idea is we're just going to do linear classifiers on top of this feature, and that's going to be our classifier. So linear classifiers are really fast. So the way this works is that we compute our histogram of oriented gradient feature for the whole image at multiple scales. And we run this linear classifier at every scale, every position. Just do it really fast. Just do it everywhere because it's a linear classifier and it's fast to evaluate. And this worked really well in 2005. Sort of people took this idea and worked on it a little bit more for the next couple years. So sort of one of the most important detection paradigms pre-deep learning was this thing called the deformable parts model. So I don't want to go too much into the details of this, but I mean the basic idea is that we're still working on these histogram of orient gradient features, but now our model, rather than just being a linear classifier, we have this linear sort of template for the object, and we also have these templates for parts that are allowed to sort of vary over spatial positions and deform a little bit. And they have some fancy thing called a latent SVM to learn these things, and a really fancy dynamic programming algorithm to actually evaluate this thing really fast at test time. So this is actually kind of fun if you enjoy algorithms. This part is kind of fun to think about. But the end result is that it's a more powerful classifier because it allows a little bit of deformability in your model. And you can still evaluate it really fast. So we're still just going to evaluate it everywhere, every scale, every position, every aspect ratio. Just do it everywhere because it's fast. And this actually worked really well in 2010, around there. So that was sort of state-of-the-art in detection for many problems at that time. So this is, I don't want to spend too much time on this, but there was a really cool paper last year that argued that these DPM models are actually just a certain type of convnet. right? So, right, because these histograms of oriented gradients are like little edges. We can compute edges with convolutions, and then the histogram is kind of like pooling, that sort of thing. So if you're interested, check out this paper. It's kind of fun to think about. Right, but we really want to make this thing work on classifiers that are not fast to evaluate, like maybe a CNN. So here, this problem is still hard, right? We have many different positions we want to try, when we probably can't actually afford to try them all. So the solution is that we don't try them all. We have some other thing that sort of guesses where we want to look, and then we only apply our expensive classifier at those smaller number of locations. So that idea is called region proposals. So a region proposal method is this thing that takes in an image and then outputs a whole bunch of regions where maybe, possibly, an object might be located. So one way you can think about region proposals is that they're kind of like a really fast class-agnostic object detector, right? They don't care about the class. They're not very accurate, but they're pretty fast to run. And they give us a whole bunch of boxes. And the general intuition behind these region proposal methods is that they're kind of looking for blob-like structures in the image, right? So like objects are generally like the dog. I mean, if you kind of squint, it looks kind of like a white blob. The cat looks kind of like a white blob. These flowers are kind of blobby. The eyes and the nose are kind of blobby. So when you run these region proposal methods, a lot of times what you'll see is they'll kind of put boxes around a lot of these blobby regions in the image. So probably the most famous region proposal method is called selective search. You don't really need to know in too much detail how this works, but the idea is that you start from your pixels and you kind of merge adjacent pixels together if they have similar color and texture, and form these connected blob-like regions. And then you merge up these blob-like regions to get bigger and bigger blobby parts. And then for each of these different scales, you could actually convert each of these blobby regions into a box by just drawing a box around it. So then by doing this over multiple scales, you end up with a whole bunch of boxes around sort of a lot of blobby stuff in the image. And it's reasonably fast to compute, and actually cuts down the search space quite a lot. But selective search really isn't the only game in town. It's just maybe the most famous. There's a whole bunch of different region proposal methods that people have developed. So there was this paper last year that actually did a really cool, thorough scientific evaluation of all these different region proposal methods, and sort of gave you the pros and the cons of each and all that kind of stuff. But I mean, my takeaway from this paper was just use edge boxes if you have to pick one. So because it's really fast. You can run it in about 1/3 of a second per image, compared to about 10 seconds for selective search. But the more stars is better, and it gets a lot of stars, so it's good. Right, so now that we have this idea of region proposals and we have this idea of a CNN classifier, let's just put everything all together. So this idea was sort of first put together in a really nice way in 2014 in this method called RCNN. So the idea is it's a region-based CNN method. So it's pretty simple now that we've seen all the pieces. We have an input image. We're going to run a region proposal method like selective search to get about maybe 2,000 boxes of different scales and positions. I mean, 2,000 is still a lot, but it's a lot less than all possible boxes in the image. Now, for each of those boxes, we're going to crop and warp that image region to some fixed size, and then run it forward through a CNN to classify. And then this CNN is going to have a regression head, and a regression head here, and a classification head. They used SVMs here. So the idea is that this regression head can sort of correct for region proposals that were a little bit off. Right, so this actually works really well. It's really simple. Yeah, it's pretty cool. But unfortunately, the training pipeline is a little bit complicated. So the way that you end up training this RCNN model is, like many models, you first start by downloading a model from the internet that works well for classification. Originally, they were using an AlexNet. Then next, we actually want to fine-tune this model for detection, right? Because this classification model was probably trained on ImageNet for 1,000 classes, but your detection data set has a different number of classes, and the image statistics are a little bit different. So you still train this network for classification, but you have to add a couple new layers at the end to deal with your classes and to help you deal with the slightly different statistics of your image data. So here, you're just doing classification still, but you're not running it on whole images. You're running it on positive and negative regions of your images from your detection data set. Right, so you initialize a new layer and you train this thing again for your data set. Next, we actually want to cache all these features to disk. So for every image in your data set, you run selective search, you run that image, you extract those regions, you warp them, you run it through the CNN, and you cache those features to disk. And something important for this step is to have a large hard drive. The Pascal data set is not too big, maybe order of a couple tens of thousands of images, but extracting these features actually takes hundreds of gigabytes, so that's not so great. And then next, we have this, we want to train our SVMs to actually be able to classify our different classes based on these features. So here we want to run we want to train a bunch of different binary SVMs to classify image regions as to whether or not they contain or don't contain that one object. So this goes back to a question a little bit ago that sometimes you actually might want to have one region have multiple positive, be able to output yes on multiple classes for the same image region. And one way that they do that is just by training separate binary SVMs for each class. Right, so then this is sort of an offline process. They just use libsvm. So you have these features. These are maybe, those aren't positive samples for a cat SVM. That doesn't make any sense. Right, but you get the idea, right? You have these different image regions. You have these features that you've saved to disk for those regions, and then you divide them into positive and negative samples for each class, and you just train these binary SVMs. So you do this for cat, you do the same thing for dog, and you just do this for every class in your data set. Right, and then there's another step, right? So then there's this idea of box regression. So sometimes